Hi, we're going to talk about rate, the beginning of rate. So rate of reaction, our official word in chemistry for that is kinetics. So if you ever hear the term kinetics, it's just talking about rate. So the rate of a chemical reaction, I want to put this into something contextual that you can relate to. I want you to think about driving a car. Driving a car, the rate at which we go is going to be miles per hour. And you know what that means. It's how many miles we cross, so the distance that we cross over a certain amount of time. So if I'm going 60 miles an hour, in 1 hour's time, I will cover 60 miles. Well, it's the same concept in chemistry, but instead of it being distance, how much distance we cover over time, it's how much has reacted. So right here, I put it's a change of concentration. And it can be change of concentration of reactants or products. Reactants, remember, over time, they're going to decrease, and products over time are going to increase. So I have a graph right here, and let's go ahead and label the two axes. So this exponential decay that you see is going to be, for the x-axis, time over time. We are decreasing. The y-axis is going to be the concentration of reactants. So I'm going to put in brackets right here, this will be our reactant. Now, I put that bracket very purposefully. The concentration that we use is molarity. We always use molarity when we're talking about rate of change. The amount of reactants that are consumed is going to be moles per liter, moles per liter. Let's see here. So I abbreviated this. Notice that delta, that's a capital delta D in the Greek alphabet. So delta means change. So a little reminder, let's write that down. So there's the word change. Here's our symbol for that. It's going to be the change of some concentration. So I just put A. We're going to call our reactant A. The change of concentration, and I wrote the reminder, this is going to be molarity, divided by the change of time. Now, the unit on this, you're going to see molarity per second. Now, seconds, I put down seconds because that's our SI base unit for time, but you'll see this in molarity per minute, molarity per hour. You could even have molarity per year, something really, really slow. So it's any unit of time, but typically we use seconds since seconds are that SI base unit. Now another way that you could see this written is with the molarity broken into its numerator and denominator, moles per liter. So another way that you'll see this is mole divided by liter times second. That's the same thing. That's the same thing. Now for me, it starts to look a little messy, and so I always rewrite it molarity per second. That's just a little bit cleaner in my brain as I'm tracking units, as I will do molarity per second. But don't be surprised if you see this. That's totally fine. Now, breaking it out, change. You'll recall that change is always going to be final minus initial. So we will have the final concentration minus the initial concentration divided by the final time minus the initial time. And then I put a little note here. We literally, if it's a reactant, because it's being consumed, it's decreasing, we will literally put a negative in front of that. And I want you to look at the significance of that negative. Let's say that this was a reactant. So I put that negative sign in front of it. Well, the final concentration is going to be smaller. You'll have a small number, let's say 1, minus the initial concentration. The initial concentration is greater. You're going to start with more than what you end with. So let's say that's a 2. So when you subtract that, you get a negative number. Oh, but wait, negative times negative, you end up with a positive rate. Now down here, time always, because time is progressing, you'll always have a positive denominator. The final time will always be greater than that initial time. So here's the outflow of it, the real significance. We always write rate as a positive value. We always write it as a positive value. Amount consumed over time, or the rate at which a product is produced over time. Notice for the product, if this was a product, I make that a plus sign. Now products, what would this graph look like if it was products? Be just opposite. You would start with 0 and it would increase. You'd increase the amount that's produced. let's see here. Or actually, it would go like this. Sorry, it would be fast, and then it would start to level off. Sorry. So you would have a really quick increase, and then it would level off. On this one, for a product, you always end up with more than you started with, so it's automatically positive. Positive times positive gives you a positive. So again, the outflow, we are going to write rate as a positive value. Well, you always write that as a positive value. Now, I want to look at this graphically. It's really good to understand the graph. Again, this is going to be a reactant, and it's going to be consumed quickly. You'll learn later on why. It deals with the collision theory. Excuse me. And so it's going to consume quickly, and then the rate at which it consumes, it slows down. Likewise, if I was to do a graph of being produced, you're going to have a lot produced at the beginning, and then the rate at which it produces slows down. So there are two ways that we can look at this. We could say, okay, at one moment, right here, at one moment, I know exactly what's that rate. At this time t, what's the rate at which reactants are changing to products? Well, that's called an instantaneous rate. And that instantaneous rate, you're maybe thinking about this. Look how I drew it. There's a tangent to the line. I'm looking at that point right there. Its rate of change over time is calculus. Now, for a first year chemistry class, even through 1210, 1220, the class that you need for medical school, a professor is not going to require you to do calculus. So this instantaneous rate, you will actually be given the formulas for the rates integrated. They will already be integrated for you, and I will give those to you. I have videos on those for you. You will be expected, however, at times to calculate the average rate. So the average rate is if we look from time 1 to time 2, so T initial to T final, I'm wondering what's the average rate? And notice how I drew that straight line. Average is going to be linear. Now this is exponential and exponential decay, so it's not going to be that exact, precise, at a moment what's the rate, but overall the average from point 1 to point 2, what was the average rate at which the reactants were consumed over time. And that right here, I have a video for average rate for you as well. So again, two ways that we can look at this graph. You can get an instantaneous rate. That's going to be calculus. Exactly at that moment, what's the rate? The integrated formulas will be given for you. Average rate is where you take 2 points and you find overall what's the average from point A to point B on reactants being consumed over time. So there you have it, a brief overview on rate of reaction. Thank you. Have a really good day.